Okay, so I'm going to finish off chapter 2 today. But before I do so, we're going to look at just going to be looking at a recap of what we spoke about last week. Okay, so this is recapping all of last week's stuff, and then we're going to go on from about page 14 in the notes. Okay, so partial differential equations made up of partial derivatives of usually multivariate functions. Okay, so unlike PDEs where you just have a differential equation with respect to one independent variable, a PDE can be with respect to multiple independent variables. In most cases, they can't be solved analytically. Okay, so therefore that's why we use a numerical approach. The approach we'll be looking at in this term is called the finite difference method, often abbreviated to FDM. And what this does is it approximates partial derivatives using finite differences, which we looked at last week. And what this does is it forms an algebraic equation, the solution of which is an approximation of the PDE. Okay, so we replace partial derivatives by finite differences. This forms an algebraic equation. We solve that equation using some method, and that gives an approximation to the PDE. The accuracy of this approximation depends upon the order of our finite differences. The higher the order, the better the approximation. It can also depend upon the step length. Okay, so the size of the step length, which we've been using H to denote up until now, the smaller that step length, the more accurate the approximation. But the problem is, if you have a step length which is too small, you have lots and lots of nodes in your finite difference grid, which we'll be looking at today. And the more nodes you have, the more computational costs you incur. Okay, so smaller step lengths means you're doing more work, but you get a more accurate approximation. So there's this sort of trade-off between computational resources or computational cost and accuracy of your solution. Okay. Okay, so finite differences, where they come from, they're derived directly from the Taylor series. A few methods we can use to derive them. Undetermined coefficients is what we looked at in this week's tutorial. What we can do is we can approximate a derivative. Doesn't have to be the first order derivative, it could be any order. Okay, about a point close to x. So here we have a number line. Okay, so this in terms of the independent variable x. This is a point on the number line, and let's say u is some function, so that's a point ux. Okay, what we can do is if we step to the left by a distance of h on our number line, we can find the value of that function at ux minus h. Or we can step to the right and we have ux plus h. Okay, what we want is to approximate the derivative at this point. And what we do is we use neighboring values. Sometimes we go 2 steps to the left and 2 steps to the right. Okay, so essentially that's what finite differences do. They use neighboring values to approximate derivatives. Okay, so the Taylor series is truncated. Okay, we do that because we can't possibly sum an infinite series. So we say, okay, we're going to stop after, let's say, the 4th term. Okay, so we truncate the Taylor series, ignore higher order terms. Okay, so in doing so, because we haven't summed to an infinite number of terms, we're going to incur some kind of error. Okay, and this error is called a truncation error, and that is expressed using this big O notation. So this just simply a big O, and in brackets some function of h. Okay, in this case it's h to the power n. What this means is, as our step length gets smaller, the error of the approximation tends to 0 is proportional to the function h to the n. So for example, if you got big O h to the 2, okay, so you've got a second order approximation, this means that as our step length gets smaller, the error gets smaller, proportional to h squared. Okay, so remember, h will be less than 1. So you sort of got a quadratic, sort of inverse quadratic profile. The higher the value of n, the quicker the error tends to 0. Okay, finite differences can be derived using different methods by rearranging the Taylor series, or more generally using the method of undetermined coefficients. So that's when you write your finite difference approximation in terms of alpha 1, alpha 2, alpha 3, etc. You substitute in the Taylor series, and you say, okay, which term do I need to disappear to 0, and which term do I want to be 1? And that's how we derive, we derive a linear system, solve for those undetermined coefficients, and that's what we looked at last week. Oh, by the way, I put up a scan of the solution to questions 1 and 2 for the lab sheet 2, and that's up on Moodle. So if you want a bit of help with undetermined coefficient, there's the solutions are up on Moodle at the moment. And finally, finite difference approximation of order n. Okay, so if we want, say, a 4th order approximation, we need 2 times n minus 1 nodes. So a 4th order approximation will require at least 4th order 2 to the n, that's 8 minus 1, 7. No, that's not quite right. Oh, 2 times n minus 1. Sorry, I've got a little bit of a typo there. Okay. Although some of these nodes may be 0. Okay, so not all the nodes will have a value. Okay, so here's a few we looked at last week. Okay, we have a 1st order forward difference approximation. So an approximation to a 1st order derivative. We go 1 step forward along our number line. Okay, so we have ux plus h minus the current value of ux, all divided by step length. And that's 1st order accurate. Okay. Or we could go backwards, which is same order accuracy. Okay. A better approximation is a 2nd order central difference. Okay, so this is still of a 1st order derivative. Okay, so this time we take the step to the right minus a step to the left and divide it by 2 times the step length. Okay, and that's 2nd order. Okay, that's a 2nd order difference of a 1st order derivative. Okay, so it's kind of, we use order, the word order, in too many places for my liking. Order can mean the accuracy, and it also can mean what derivative we're looking at. So it's quite easy to get confused with that. So for example, this one at the bottom, this is an approximation of a 2nd order derivative because we got xx in the subscript, but it's an accuracy order of 2. Okay, so you can get a bit confused. So it's a 2nd order derivative, a 2nd order accurate approximation of a 2nd order derivative. Okay, and that's what we call a symmetric difference.
When you get to this one, you're using the 2nd order central difference.
Sorry? This one down here.
Yeah.
It can also be referred to as a central difference, yes. Essentially, symmetric means, are we symmetric about the ux term? Okay, so we got 1 times the left-hand node, and we have 1 times the right-hand node, so we call that symmetric. This one here, the central difference, is also symmetric, just to confuse you. Okay, if it looks symmetrical about the ux node, we can call it a symmetric difference, or often it's called a central difference. I've referred to this one as central difference because that's what seems to be more generally referred to in textbooks. Okay, so symmetric and central tend to be sort of interchangeable. They mean the same. Okay, so that's just recapping last week. Okay. What we're going to be looking at this week is what we call a finite difference toolkit. Okay, think of these finite differences as tools. Okay, so if you have a job to do, okay, you want to fix your car, you have a tool set there, you pick the right tool for the job. Okay, that's exactly what we're going to be doing here. So we have a PDE. Let's say we have a 1st order derivative in the PDE. Okay, we pick up from our toolkit, we pick up a approximation to a 1st order derivative. So that's why we call it a toolkit. One thing I'm going to introduce here is the idea of subscript notation. Okay, this notation here, it's a bit long-winded. Okay, in mathematics we're quite lazy. We like things to be quite easy and simple to write down. So what we tend to have is our PDEs are in the form of a multivariate function. So here we have a function which is of the independent variables t and x. T normally means time, x normally means space, but that's by no means for every case. Okay, so our PDEs sometimes will be in partial derivatives with respect to time, sometimes they may be in partial derivatives with respect to space. So, for example, if I was to find the partial derivative with respect to time, because it's a partial derivative, x remains constant. So in this case, I've used a central difference. Notice nothing happens to the x variable. Okay, it's only the t variable which I step. So I step in terms of the t variable, and I've called the step length delta t. So that's a change in t. So x is constant. I've examined what is the change in this function u with respect to t. And this is using a second order in time derivative, approximation, sorry. Alternatively, if I have the partial derivative with respect to x, t remains constant. So here you notice nothing happens to t. Okay, it's only in the x in which I step. So I step forward in x and backward in x divided by 2 times the step length. The step length in x is delta x. Okay, so the top one is a derivative in time, and the bottom one is derivative in space. Okay, that's a bit of a mouthful, or a bit of a complicated thing to write. So what we do is we introduce a superscript notation. Okay, the subscript I denotes the ith node in space. Okay, so subscript means space, so along the x direction. The superscript n means in time, means a time level. So this uin means a value of u at time tn and at space or at node xi. Okay, so the subscript means the spatial index or the spatial node. The superscript n means the time level. So for example, okay, this top finite difference approximation could be written like this. So you notice in space, the node is the same. We're still on the ith node. But in time levels, we have the n+1 time level minus the n-1 time level. So n+1 is sort of analogous to t plus delta t, and similar with n-1. And likewise with the spatial derivative, here, notice that both on the time level n, so we're not stepping forward or backwards in time at all, but we're stepping one to the right, one node to the right, minus one node to the left. Okay, so superscript and subscript notation is just used just to simplify the writing down of the finite difference approximations. With that in mind, we can do the same for all our other finite difference formulae. And the table on page 14 gives us what we call our finite difference toolkit. So these are all approximations. Okay, the forward. Okay, so forward difference means we step one node to the left, so the i+1 node minus the current node, the ith node, divided by the spatial step delta x. Okay, that's exactly the same as the forward difference which we've been using. That's forward difference and it's first order in space. Okay, the accuracy is first order in space. Backwards difference, similar, except for we go to the i-1 node. And again, that's first order in space. Okay, so all of these here we've derived last week. Notice the T1s are very similar, except for we change the superscript. Okay, and the subscript remains constant. Okay, and you could do the same with any order. You can go up to, you know, we've looked at fourth order symmetric differences. You can have skewed order. I mean, sorry, not skewed order, but you can have skewed differences, so one-sided. Okay, but these are the sort of general ones, and you should be able to remember these. Okay, so this is our toolkit. This is what we select from in order to approximate our partial derivatives. Okay, with this toolkit in mind, what I'm going to look at now is an example finite difference scheme. So how do we go about solving a partial differential equation? Okay, part of this is going to be done by hand calculation, and then what I'm going to do is, after we've done the hand calculation, I'm going to show you a step-by-step guide way to produce a MATLAB program to do the same calculation. Okay. Okay, so this is the an example, a work through of solving a PDE using a finite difference scheme. And the PDE we're going to solve is called the advection equation. It's a hyperbolic type equation. We're going to be looking at this in more detail in a few weeks' time, but for now it's just quite a simple PDE. This models advection. It models transport of some substance along a channel. Okay, so just models pure movement, doesn't model anything else. So what we have is we have a spatial domain of x is in the range a to b. So we start x at a and we end x at b. Everywhere in between is in our spatial domain. So we want to be able to solve between x, from x equals a to x equals b. In this case, t is time. Okay, so we have ut. Okay, so here we have, oh, where's my pointer gone? Right, we've got ut. So the change of our value of u over time plus v, which is velocity. That's how fast does our substance move down the channel, multiplied by the change in the substance over space. So first order derivative in time plus velocity times second order first order derivative in space. And that equals 0. So that's our advection equation. U is a concentration of some pollutant. So think of it like a river. If you've got a river, you put some pollutant in the river, that's going to travel down the river. Okay. If the river, the velocity is measured at v, you could then model what's going to happen to that pollutant. V is advection velocity. Okay, u, t, x. So u is some function which is in terms of the independent variables time and space, t and x. When t is equal to 0, we have our initial conditions. Okay, what does u look like at the beginning? If our initial conditions is some function of x, okay, the solution, so there are exact known solutions for this PDE. That's unusual for PDEs, but we have an exact solution. The exact solution is the function of x plus velocity times t. Okay, in other words, it's moved some distance down the channel. Okay, remember, velocity times time gives you distance. Okay, so we know there is some solution to this equation. Okay, so that's the equation we're going to solve. First thing we need to do is what we call spatial discretization. We have our spatial domain. It's between x equals a and x equals b. We need to split this up into a number of different points, and these points are called nodes. Okay, so at the lower boundary, x equals a, we label this x0. Now, this is a bit of a contentious issue here. I've used x0 because that's what's most common in textbooks. Some people use x1. x1 would be more helpful because it's easier in MATLAB, but what I decided to do is go for what is most commonly used. So sometimes you may see the lower one in terms of x1 in some sources, but I've used x0. So bear in mind that it doesn't really matter what you use, but for these notes, I'm always going to use x0. Okay, so the node at the lower boundary, we label this x0. Okay, the node at the upper boundary, so that's the upper bound of our domain, we label xn. Okay, so big N. Okay, so this is at B and xn. The first node in from the lower boundary, we label x1. And this is distance delta x away from x0. Okay, so delta x is the step length. So x0 is the left-hand bound or the lower boundary. X1 is one step length in from that lower boundary. And we keep doing the same thing. The second node in from the lower boundary is one step away from x1. So we've labeled the second node x2. And the coordinate of this second node is a plus 2 lots of delta x. Okay, and we keep going until we reach top boundary. Okay, so you can see the number of nodes is determined by this spatial step. The bigger delta x, the less nodes we're going to have. The smaller delta x, the more nodes we're going to have. Okay, so we need to calculate how many nodes we have. Okay, so what we need is at this upper boundary b, we need it to be equal a plus n times delta x. Okay, because notice that when we have x2, it's 2 delta x. When we have x1, 1 delta x. Okay, so we need this to happen. We know what a and b are. If we know what delta x is, the number of nodes is simply b minus a over delta x. Alternatively, we may not know what n is, but we do. Sorry, we may not know what delta x is, but we know what n is. So if you're given the number of nodes, then you can work out what the spatial step is. You might recognize this from the first question I got you doing on that MATLAB revision sheet. It's exactly the same. Okay, so sometimes you'll get told the step length and you've got to work out n. Other times you'll get told n and you work out the step length. Okay, it's up to you, really, but they're both done in the same sort of method. Okay, so that's discretizing the domain. You choose how many nodes you want to approximate. Okay, so once you discretize the domain, what we can do is we can form a finite difference scheme using finite differences. So this is our PDE. We have two partial derivatives, one with respect to time, first order with respect to time, one with respect to space. Okay, you can replace them with anything you want. It's up to you. Okay, within reason, anything you want. It will depend upon how accurate you want to be. It will depend on a number of things. But for the first example, I'm going to say, okay, we're going to replace the derivative with respect to t by a forward difference from our toolkit, and I'm going to replace the derivative with respect to x using a backwards difference. Okay. Sorry. If I chose a forward difference here, we'd come up with some problem. The reason being is what we're doing is we're modeling a transport down a channel. So let's say if v is positive, we're going to start, let's say we have some substance starting here and it's going to move down the channel. If we were to use a forward difference, what we'd have is we wouldn't know, because the substance is moving in this direction, we're using the node to the right. Okay, so it's not going to know when that substance reached a particular point. You sort of understand. I mean, I'll cover this in more detail in a few weeks, but if v is positive, we must use a backwards difference in this case. Okay, I'll explain this a bit more when we do with hyperbolic equations, but there's a reason why I chose a backwards difference. We could have used a central difference, could have, but I wanted to make things simple to start off with. Okay, so essentially, it sort of matters what we choose, but for now, we're going to just choose a forward difference and a backwards difference. Okay, so this is from our toolkit straight into here. What I've done on this step is I've rearranged this to make the n+1 term the subject. Okay, so what we're going to do is you have initial conditions. You want to solve for the next time step. Okay, so if we rearrange to make u n+1 the subject, this is the next time. This is the next value in time using all previous values. So you notice that the superscript here are all in terms of n. So we know what those are. We always know what the n values are. We want to calculate the n+1 value. Okay, and this gives us our finite difference scheme. So this approximates solution at the next time step using current values. This is another step which isn't strictly necessary, but it does help in presenting finite difference schemes. Because this is an approximation, we write big U as little u, just to say, okay, we know we're not solving u exactly, we're approximating u. Not all textbooks do this. It's just kind of almost it's almost a personal preference, but I like to do it because it shows that it's an approximation. And because we use first order forward difference and first order backward difference, our error term is first order. Okay, so we have an error term which is based upon delta t and delta x. Okay, this is what we're going to use to solve this equation. So this is our finite difference scheme. Okay, what I'm going to introduce now is the idea of a finite difference stencil. What does our scheme look like? Okay, and a finite difference stencil is just like a way of sort of graphically showing what your scheme looks like. Okay, so I've written out the scheme again up here. Okay, and this is what we call a finite difference grid. Okay, along the horizontal axis we have space. Okay, this is our x-axis, and on the vertical axis we have time. Okay, so at the beginning, all of these nodes, which are represented by these little circles, we know what the values are of u at those nodes. Okay, so this is the nth time level, so I know what these values are. These values here on the n+1 time level, I want to calculate using this. Okay, so let's take one node, node I. Okay, so this node here depends upon the value of uin and also ui-1n, so one to the left. Okay, so what we do is we highlight these nodes, and you can see I've drawn a thickened line between them. This is what we call a stencil. It allows us to sort of understand how we're calculating this. So we're calculating this from the previous time step, from the previous value, and the previous value one to the left. Okay, that gives us a finite difference stencil. Quite often we don't bother with all of this axes and stuff. Later on, when we do hyperbolic and elliptic PDEs, you'll notice I start drawing finite difference stencils without all of this other grid. You just have this sort of darkened region here. Just allows us to understand how this value here is calculated. Okay, looking at this stencil, what happens if I want to calculate, say, that node there? Okay, I'm going to use that node, and I need to go one to the left. But there's nothing there. It doesn't exist. This is outside of our domain. So we've got a problem here. Okay, this is sort of introduces the idea of boundary nodes. Okay, so the finite difference scheme on the previous slide, we require values of ui and ui-1 to calculate the next value of ui. What happens when we're at the lower boundary? So what happens when I is 0? Okay, so if I replace i's with 0, we get this one here. Okay, u-1. That doesn't exist. We're right on the edge of our boundary. So what I mean by that is there's u0. There's nothing existing over here. This is outside our domain. So we can only calculate our finite difference scheme for nodes u1 up until un. Okay, because we need the value to the left to actually calculate all of these. So what we do is we label these computational nodes. If I had a central difference formula, a central difference in space, there would also be using a node to the right. So if we're at the upper boundary, I'd need a node somewhere in this region, which I haven't got. So that's why the computational nodes extend to un-1. Strictly speaking, using this scheme, they should extend to the boundary, but that's not always going to be the case. Okay, so computational nodes, in this case, extend from the first node in from the boundary to the penultimate node. Okay, so we call those computational nodes. That's what we can calculate the solution for. U0 and UN on the boundary are called boundary nodes. We can't calculate their solution using a finite difference scheme. What we do is we define them by using some form of boundary condition. What sort of behavior do we want to have at the boundaries? And that will give us a boundary condition. Okay. For now, for this example, I'm going to just set these nodes equal to 0. Just make it easy. Okay, so what we're going to do is going to look at a hand calculation. So in a minute, I'm going to get the calculator out and get sort of calculating some of these. Okay, so what we're going to do is we're going to define our domain, and our domain is going to extend from 0, x equals 0, to x equals 1. I've set the velocity to be 1, and I'm going to have big N to be equal to 10. Okay, so that means each spatial step is 1/10. Okay, so b minus a over n, or b is 1, a is 0, n is 10, which gives us a spatial step of 0.1. That means we have n plus 1 nodes. Okay, we have 11 nodes. x0 is 0, x1 is 0.1, 0.2, etc., all the way up to 10. Okay, so each of these nodes, the darkened nodes, the computational nodes, we can calculate what the solution is. The nodes on the end, which I've left white, are boundary nodes, and what we're going to assume is these are always going to be 0. So but the boundary conditions are always 0 at the first and last node. Initial conditions, what's the initial value of these nodes? Well, I've defined this exponential function. And if you remember from the first lab sheet we did, we calculated this in MATLAB. Okay, this is just some Gaussian curve. Okay, so that's a hand calculation. Right, so I think this is all on page 17 now. Okay, so first thing we could do, calculate the initial conditions. What's our first value when n equals 0? Okay, for the 0th node, u0, we've got a boundary condition. That's always going to be 0. Okay, for the first node in, the x coordinate of that first node is 0.1. So instead of x, we put 0.1 there, calculate that, and we get 0.0001. Do the same for 2, 3, etc., etc. Okay, so that this function here gives us our initial conditions. We need these in order to solve this PDE. Okay, so we can calculate the initial conditions. In this case, delta t and delta x are constant. Okay, this won't always be the case, but for this PDE they are. So we can calculate, if I go back a couple, we can calculate this v times delta t over delta x. We can calculate that. That's going to be same for all points. So might as well calculate it once at the beginning. V is 1. Delta t was 0.05. I've set that. And later on in the term, we'll explain why I've set it to be 0.05. Divided by the spatial step, which is 0.1. Okay, so v times dt over delta x happens to be 0.5. Okay, now what we do is we solve for the first time level. Okay, so the scheme is ui minus v times dt over delta x, which is a half, times ui minus the node to the left. Okay, all you do is you insert the back values into those and you calculate the new values. Okay, and there's this incomplete table over the page. Okay, on page 19 there's this incomplete table. What we're going to do now is we're going to calculate those values which are missing. Okay, so a bit of work for you to do now. Right, so I'm going to just switch to the camera. So if you are watching this at home, it's tough luck there. Right. So what we're going to do is I've deliberately left a few of these blank so we can fill them out now. So this one here, this is we want to calculate U3 at the first level, time level. Okay, so we're going to calculate this one here. The level above, that's the initial conditions. Okay, so this level, this line above, that was calculated using that exponential function. This is one time step in. So remember the time step was 0.05. So this is the solution at t equals 0.05. Okay, we're using the, if you recall, the scheme was you take the value from the previous time step. So we got u0 as opposed to u1 minus v dt over dx, sorry, v delta t over dx multiplied by the previous value minus the value to the left. Okay. So all we do here is we just substitute in our values. So U3 is 0.3679 minus a half, because we just calculated that on the slide. Oh, sorry, is that showing up very well? Zoom in a bit. Okay, U3, which is 0.3679 minus, and the one to the left, which is 0.0183. Okay, so a bit of number crunching. Minus 0.5 times 0.3679 minus 0.0183. And we get 0.1931. Actually, I've calculated that on page 18. I forgot to delete that one from page 18, but it's there. Okay, so what we can do now is we can fill in that missing gap. Okay, now we can calculate this one. Okay, so this one is U4 at time step 1. Okay, that equals U4 at time step 0 minus V times delta T over delta X, U4 minus 1 to the left, which happens to be U3. Okay, so we substitute in these values. So the previous value was 1 minus 0.5 times 1 minus, and the value to the left was 0.3679. Okay, so grab your calculator, do the sums. That's 0.6840. I've rounded to 4 decimal places there. Okay, so let's see if you can fill out all the remaining ones. Okay, I'm not going to do it for you. You can, if you can give it about 5 or 10 minutes to fill out the remaining ones. Yeah. Technically speaking, you should use the unrounded value. Technically, yes. So, I mean, I've used 6840 on this one here. Technically speaking, I should have used 6839, blah, 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 to how much accuracy I had in the calculator. Yeah, but yeah, you would do that, else the rounding errors would accrue. Yeah, if you want, yeah. In other words, I should have, yeah. Yeah, that's a good point. Normally, when we write down solutions, we round to a particular decimal place. But as we'll see in a minute, we should always work to. You should really use memory functions in calculators and computers, but I haven't. Okay, so let's have a look at see what some of these are. Then you should start to see a pattern in the calculations you make. Okay, so you start to see the pattern. It's the previous one minus a half times the previous one minus one to the left. Okay. This exercise is deliberately meant to be tedious. I'm trying to show you something. Okay, it should be sort of obvious, but we don't. This is not how we solve PDEs. Okay. Hand calculations are only really used to check our programs work how we want them to. So they are useful. I mean, you notice I've only used 10 nodes here. Sorry, 11 nodes with 2 boundary nodes. Usually we use hundreds or thousands, sometimes hundreds of thousands. But hand calculations, we calculate the solution using a reduced number of nodes. Then we can check, if we do program a computer to do this, we can check our program works based on our hand calculation. In fact, I'm so bored already, I'm not going to carry on with those, calculating them. I've got a short attention span, what can I say? Okay, so that's a hand calculation. Is everyone okay with that? Okay, so we derive the finite difference scheme by replacing derivatives with finite difference approximations. We rearrange them so that the n+1 term is on one side and all the n terms are on the other. Apply some boundary conditions and initial conditions, and then we solve. Okay, that's incredibly tedious doing it by hand. What I'm going to do now is create a MATLAB program to do this. Okay, so, oops, I'm not even on the computer here. And what I'm going to do now is I'm going to start totally from scratch. So I may make mistakes, I may get bugs and errors and things like that, but bear with me if I can find, where's MATLAB? There we go. Okay, I'm going to call my program finite difference scheme example. Okay, so what I'm going to do now is I'm going to show you from scratch how we program this finite difference scheme in MATLAB. I'm just going to undot this because I don't like it docked. Okay, what's the first thing I should do when I start any program? CLC, and what else? I tend to think of it as clear workspaces. Okay, make sure you're starting with clean slate. So CLC will clear the command window. Not absolutely necessary, but it helps keep things tidy. clear or just wipe everything from the memory. So nothing's going to contaminate our program. Okay, the next thing I'm going to do is I'm going to define variables. Okay, so I'm going to define all of my variables. I think we start with n was 10, wasn't it? So n was equal to 10. And what I tend to do is just have a little note, say what it is. So this is number of nodes minus 1. But remember, n is always 1 less than the number of nodes you have, because we start at 0, x0, and we go up to xn. So we're going to have 1 plus n number of nodes. What else have we got? We've got a, which is the lower bound. So lower bound of the domain. And we've got b, which was the upper bound of the domain. Okay, so if I know a, I know b, I know n, I can calculate the step length. So delta x, I use dx to shorthand for delta x. And that's b minus a over n. Oops. So that's the spatial step. In this particular example, the time step was given. The time step was 0.05. Okay, so that was just given. Sometimes we may need to calculate it, and that will come later on in a later lecture. Have I got anything else? Have I missed anything off there? So any other bits of information? I may come back to that bit. I might have missed them out. So the next step, what I'm going to do is I'm going to define the spatial array. By this I mean, what are my x coordinates? Okay, so remember the first question I gave you on that first tutorial sheet was give me a list of 12 numbers going from 1 to 5 in equal steps. It's exactly the same thing here. So my x array goes from the lower bound at a in steps of dx up until b. Okay, so that's the x coordinate of my finite difference nodes. So that's the discretizer domain. I need initial conditions. Okay, so define initial conditions. I can remember what this is. I might need your help here. I'm going to call it u0. So u0 is going to be my initial values of u. Okay, from memory, is it exponential minus 100 times x minus 0.4? Is that right? Yeah. What I'm going to do here is use a dot power squared. Okay, remember x is an array. This has got 11 numbers in it. If I was just to raise this, if I was just say, okay, x squared, that would try and multiply a 1 by 11 matrix by a 1 by 11 matrix. It can't be done. So in MATLAB, we put the dot in front of the power to say every element of this array is raised to the power 2 separately. Okay, so I think that's defined everything. Okay, that's the starting values I need. Okay, so what I'm going to do now is we calculated 3 steps. So I'm going to calculate 3 steps of the finite difference scheme. So I'm going to use a for loop. I'm going to use n for my steps. Okay, little n, just to be consistent with the nodes. Okay, so I'm stepping through 3 iterations. And just going to end that just right now so I don't forget later. Okay, so put a few, zoom out a bit. Okay, so I'm going to step through 3 iterations. What I need to do first is for each, if you look at this table, for each one we step across. So we start at the first one and we go across. So I need to loop through each of these nodes. Okay, now the nodes start at 2. Right, this may seem counterintuitive. Okay, actually what I'm going to do is I'm just going to comment that out and then run that program. Okay, so I've run the program. There's my X array. Okay, there's my X array. and there's my initial conditions. Okay, I have 11 columns here. If I say, okay, what's my x1 value? That's 0. Okay, so in MATLAB, arrays are indexed from 1 upwards. In the mathematics, as we've written it down in the notes, I've said x0 is my first value. So this first computational node is going to be x2. So it's not the first node, it's the second one. Okay, so I'm going to loop, I just uncomment this. I'm going to loop from 2 to n minus 1. So I'm looping through all of my computational nodes. Actually, I ought to write that. So loop through the computational nodes. Okay, I'm going to end that before I forget. Right, now I type out the finite difference scheme. We need a name for our newer values of n, newer values of u. So I tend to use unp1. That stands for un plus 1. Just the way I do it. You can use anything you want. It doesn't matter. It's up to you. I tend to use unp1 to mean un plus 1. These are my next values of u. Okay, so I'm just going to. Okay, so the finite difference scheme was. Oh, I should also say, okay, u is going to be my current values of u. Okay, so u is my current values of u. So what I've done here is I've set u equal to the initial conditions to start off with. Okay, so un plus 1 I is equal to ui minus b times dt divided by dx times ui minus ui minus 1. Okay. That's the finite difference scheme what we've used. Okay, so that will loop through all the nodes, ith node, calculate what the new value is going to be. Okay. What we have to then do is update t and u. Okay. Oh, I haven't defined t yet, have I? So going back to the top, t is my time, so I'm going to start it at 0. Okay. So I have defined t. Oh, thank you. And v is velocity. Oh, that would have, yeah, so I would have come a cropper there if I'd have tried to use v. No, you're right, it's 2 to n. That was a mistake. The reason being is, in the mathematics, we go from 0 to n. Okay, MATLAB uses, it can't start an array at 0, it has to start an array at 1. So we have to add 1 on to each of those subscripts. Okay, so xn in the mathematics is xn plus 1. So the last computational node is n. So that was a mistake. It would still run, but it wouldn't calculate the penultimate node. It wouldn't calculate the last computational node. It would just finish before you got to there. Okay, what we were doing, update t. So t is equal to t plus delta t. So we've added 1 time step. So therefore I add 1 time step to t. And what I'm going to do is set u equal to un plus 1. So for the next time around, I've updated u. So when we finish one iteration, that u contains the solution at that value of t. Okay, yeah, so that will run. Okay, this program will run. It will give us well, it won't give us an output because we haven't told it to give us an output. So what I'm going to do now is I'm going to write an fprintf command, which gives us an output for this. Okay, so I'm going to output solution, output current solution. Okay, what I'm going to do is try and sort of mimic this table. Okay, so I need to loop through all of my nodes. Forgot, I just need to say un+1 equals u there. So I'm going to loop through all of the nodes this time, not just the computational nodes. So here, I only loop through the nodes which I could calculate. Okay, here I want to output them all. So I've included the boundary nodes. So the node at I equals 1 and n+1. And I'm going to use an fprintf command. How many decimal places do you want it to? Up to you. 6. Do it to 6. All right. So let's say 8.6f. You all familiar with the fprintf command from the first year? Okay, so %8.6f means I'm outputting a number. It's going to take 8 columns to display the number, and it's 6 of those columns are going to be after the decimal point. So in other words, it's a 6 decimal place accuracy. Okay, and what I want to output is UI. Okay, don't do that. And at the end, I need another fprintf just to go onto the new line. So new line. I've got no idea whether this is going to work or not. Okay, so it's probably come up with some error. We'll have a look. Okay, so I've run that. Okay, it's given me some answers. Because I've got the font size set up quite high. I mean, it's gone off the side, but you can see, yeah, it's given us some answers. Are they correct? Okay, well, this is compared to the one in the table 2.2. That table was to 4 decimal places. This is to 6. So if I cut this down to 4 decimal places instead and run that, there you go. Get what you calculated in that table. Okay, so if I was to scroll across, oh, I don't think I can. I just move this across a bit, make it a bit bigger. And you can see, if you did calculate those before, those are what the answers are. That's quite ugly output. Okay, I haven't a clue what each of these means, so I'm going to tart it up a bit. I'm going to make it look a bit nicer. So the way to do that is before we go into this step, before we even enter the solver loop, I'm going to output some column headings. Okay, so I'm going to output column headings. Okay, so I'm going to loop through equals 1 to n+1. So I'm going to loop through all of my nodes and output a column heading corresponding to that node. Okay, so I'm going to say fprintf, few spaces. This is kind of trial and error, this bit. I'm going to say u, and I'm going to output the integer number I. So this is going to be u1, u2, u3, etc. Actually, I'm going to output the number ui minus I minus 1, so it's consistent with the mathematics. So fprintf, and I'm going to put a carriage return here. Actually, I'm going to put a carriage return followed by a load of. No, I'm not going to do that. I'll just mess things up. Okay, so I run that again. There you go. Okay, so now I've got the column headings on top. Okay, and I would probably need a space just in front of it just to make it look a bit better. There you go. Okay, so remember U0 is the boundary node. So that's always 0. Okay, and as we go up, that's the solution. So that's 3 iterations of that solution. Okay, well, looking at numbers doesn't exactly tell you much. So what I could also do is I could graph this. Okay, so what I can do is after I've calculated everything, why don't we plot x against u? Okay, and see what the solution looks like. Okay. So that's what our solution is. Okay, that's after 3 iterations. That's the solution after 3 iterations. What I could also do is plot the solution at the beginning. So remember, what I could do is plot x against the initial conditions. hold on, and then hold off. So that was our initial condition, this sort of spiky one. Actually, I'll plot it using a different color. I'll plot it using red. There we go. So the spiky one was our initial condition, and the blue one is what we solved after 3 iterations. The actual solution to this should have the same shape as the red one, just moved along a bit. So this is an unusual one. It can actually calculate the exact solution. So why don't we do that? So the exact solution is equal to central function minus 100 times x plus t times v, okay, minus 0.4. Okay, this is the actual solution. So let's plot the exact solution as well. And I'll plot that in blue dashed line. Okay. Oh, gone the wrong way. Probably t minus v then. There we go. That blue dashed line should be the actual solution. Okay. So we can see we've lost some accuracy because remember this is only first order method. Okay. So the blue dashed line is the actual solution. The red line is the initial conditions, and the blue solid line is our computer solution. Any ideas how I improve on this? What can I do straight away which will improve the accuracy? Step lamp, yeah. So I've got 10 nodes, or 10, I've got 11. What should I change that to? 100? 101? Okay. Run that. There you go. Ooh. Something's gone. I don't think that exact solution, I'm going to just take off the exact solution for a sec. Okay. I'm just going to take off that. I think that's gone a bit weird. Oh, no. Okay, fair enough. Okay, there's our computer solution. Oh, I know what's happened. Right, I'm not going to ask you, Alex. You probably know what's happened. But okay, that's the red line is our initial conditions. You can see it's nice and smooth. The blue line, what's happened is it started to blow up. Okay, if I was to carry on solving this for a few more time steps, let's say 10. Okay, you can see we're starting to get oscillations. This is an example of an unstable scheme. I didn't want to show you this just yet, but okay, not all schemes are stable. And the reason why this is unstable is because, I return that to 3, is because this value of the time step is too big. Okay, that's far too big there. So what I'm going to do is I'm going to reduce that by 1/10 and then run it again. There you go. Okay, so I've reduced the time step to 5 in 1,000th. Okay, so in order to get to the same position as I was when I had it times by 10, I've got to do 30. I've got to do 10 times the number of steps. Okay, so there you go. So that's the solution using 100 nodes instead of 10. Okay, and you can see this this red line should have moved along. So I'm just going to replot the exact solution. Okay, that dashed line is the exact solution. The solid blue line is the approximate solution. You can see we're still getting a difference. So even though we've increased the number of nodes, we're still getting a difference. It's a first order scheme. It's going to be rubbish. Second order scheme would be a lot better. Okay. Right, so imagine having to calculate all of that. And if I just show you what all of those. Okay, there are 30 of them going down, and there are about 100 going across. Okay, that would take you forever. Well, not quite forever, but take you a long time to calculate all those. That's why we use MATLAB. Okay, it automates things and makes things a lot easier. Although it's important that we check that our solution matches the hand calculation. Okay, so we write our program, check our program matches the hand calculation. If we're happy it's doing its job, then we can start playing around with more nodes and seeing what happens. Okay, right. So that sort of concludes the second part of the chapter. I said at the beginning I was going to talk about the, where are we? Okay, I was going to talk about the lab sheets. Okay, right. So if I'm going to just go back to Moodle here. Okay, lab sheet 2 is what you've been working on this week. Okay, so by now you should have all have done questions 1 and 2. I think we covered those during the tutorial. Okay, so what I wanted you to do now is, given the function cos x, I want you to approximate that using first, second, and fourth order difference approximations. So there's your fourth order, that one there. First order could be the forward difference, or it could be the backwards difference. It's up to you. And use the central difference for your second order. Okay, so that's for a single node. That's not like what we just done for multiple nodes. That's only for a single node. And use a step length of 0.5. Halve the step length, calculate them again. Halve the step length, calculate it again, and keep going until the step length is, I think that's 1/32. Okay, calculate the absolute error between the exact value. I've not told you what the exact value is. I've left that for you to work out. What's the derivative of cos x? Minus sine x. So it'll be minus sine pi/2 would be the exact value. And produce a plot of the absolute errors against the step length. Okay, what you should see is the errors for the first order, the errors for the second order, and fourth order get steeper. Okay, those error lines get steeper because they're more, fourth order is going to converge to the true exact value quicker than the other two. Okay, this is the number 7 is the important bit. Okay, I want you to write a short report. I'm not looking for massive amount of work here. Okay, no more than 3 pages in length. Okay, so I've sort of restricted it to 3 pages so that you're not writing War and Peace, essentially. Okay, I don't want a huge amount of work. Yeah, so write a short report that presents your analysis. Okay, from questions 3 to 6. The report should adhere to the structure, formatting, etc. But we spoke about in the first week. Now, if you can't quite remember all of that, okay, I've put up a guide to writing maths papers. Okay, have a read through that, which is there. Oops, got that one. And I've put a couple of examples. So these are some examples which I've done. Don't copy these. You know, you might be better at writing than I am. So, you know, don't copy my style, or don't sort of copy them exactly. But they give you an idea of like the structure, formatting. For example, there's an abstract at the beginning. If you do put in a plot should have a figure caption. Mathematics should be correctly presented. Tables, etc. Okay, so that's what I wanted you to do. Oh, that's what I want you to do for the lab sheet 2. You won't be happy with your first report. No one ever is. Okay, the idea is in term 2 we get you to do a report for real, and that's worth 40% of your unit mark. We want you to have practice in doing all of this. Okay, so that's why we're doing it. Once you've done your report, if you do it in Word or LaTeX, that's fine by me. You need to upload a PDF of the report using this link here. Okay, lab sheet 2 submission and peer review. So click on that. Okay, oh, it looks different for me because I'm an instructor. I just changed myself to be a student. Okay, switch to student. Okay, so if I click on there now, start preparing your submission. You click on that link, and there it gives you, give it a title. Okay, click and drag your file to this region, save changes, and that will submit it. Okay, you've got to do that before Wednesday. So as well as doing your terms of reference, you also have to do this. And remember, you have the Monday and Tuesday tutorials to do this in as well. Once everyone's done that, hopefully you've done it before 5 o'clock on Wednesday. What's going to then happen is you'll each receive 3 reports written by other people in the class to actually mark. When I say mark, none of these marks contribute to the final unit mark. Okay? They're just purely a guide to know how you're doing. Okay, and there'll be marks out of 5, 5 good, 1 bad. Okay, so things like mathematics, is that, you know, is it correct? Is it well written? Okay, so that if you think it's really well written, you mark them 5. If you think they're crap, you mark them 1. Presentation is another one, structure, etc. There's only about 5 of these, 4 or 5. So it's not, I'm not asking you to sit down for hours and doing it. It's sort of like a 10-minute exercise. Once you've done that, the following week, you'll get a numerical mark back based on how well you did. Okay? I'm expecting you to do 4 of these this term, get you into the idea of creating reports, writing them, and also peer review. Okay, when you peer review somebody else's work, you also learn. They may have done something you've never thought of. Okay, so that's also a learning process. Are there any questions regarding these lab sheets? No? You sure? Okay, well, okay, you know, if you don't want to ask now, by all means, sort of pop by my office during my office hours or ask me in the... Yeah. The log stuff? Have I not put it on Moodle? Good question. I don't think I have. This thing. Right. So I can't remember what I've done from one week to the next. So we'll see what this gives. Oh yeah, thanks for that. Yeah. So there's a log scale. Yeah, I just mentioned about this. This is a plot on the y-axis. Oh, sorry, on the horizontal axis, I've got log of the step length h, and on the vertical axis, I've got log of the error. Okay, why have I taken log? Well, if I've done that so that it linearizes each of these lines. Okay, the gradient of these lines give us the approximate order of that approximation. So these 2 lines have got a gradient of approximately 1. So it's first order. This line here has a gradient of 2 because it's second order. And this line here has a gradient of 4, so it's approximately fourth order. The log command is there. It's the same as plot. You just write log. And that will automatically plot h against the error on that log scale. For questions 3 through to 6, if you want to use this code, which is up on Moodle, you'll have to change these things instead of the exponential function. You've got cosine. You can use that, or you can write your own. I don't mind. Okay, so it's up to you. So is that, Alex? Does that sort of answer your question? Any other questions regarding these things?
I want if you want us to do the first order, second order, fourth in the report, we have to write the derivations for everything.
That's a good question. No, I'm not expecting you to write the derivations. Okay, you can merely say the first. You can say something like the finite difference approximations are, and then you can reference. So if you find a textbook with them in, or the lecture notes, or a web page, you can then reference where you got them from. If you wanted to include the derivations, you could put them in the appendix. Okay, the appendix of a report doesn't go towards the page count. Okay, so if you really wanted to put them in the appendix, but I'm not expecting you to. Any other questions? Got another 40 minutes. I can keep you here if you want. Okay, then I think we'll call it time then. Right, next week I'll be looking at elliptic equations. Okay, so make sure you submit that report by Wednesday. Between Wednesday and next Friday, you can have a bit of a read of the elliptic equations chapter. Okay.